You know that thing you do before a high-pressure moment? Like rehearsing a difficult conversation in the shower or visualizing yourself sinking that basketball shot before you even move a muscle? That is called mental simulation. It's a superpower of the human cortex. For decades, robots couldn't do this. They were mindless followers of code. But researchers just cracked the code on machine imagination. They built a system that allows a robot to look at a new task, dream up a video of itself succeeding, and then reverse engineer the movements to make that dream a reality. Today on Cortex and Code, how robots learn to daydream. The problem, the comfort zone. Here's the psychology of the old robots. They were trapped in what we call in-distribution scenarios. Think of this as the robot's extreme comfort zone. If you trained a robot to pick up a red cube and you gave it a blue cylinder, it would have a panic attack. It couldn't generalize. The out-of-distribution zone, the unknown, was impossible because teaching a robot to handle the unknown required thousands of hours of expensive physical practice. To fix this, researchers needed a way to give robots life experience without actually making them live it. The solution? They gave the robot access to our collective unconscious, the internet. The breakthrough: synthetic mirror neurons. Humans have mirror neurons, brain cells that fire just by watching someone else do something. The internet is full of mirror neuron fuel. Billions of hours of egocentric data, videos filmed from a first-person perspective, cooking, crafting, fixing things. The breakthrough was realizing that if you build a robot with human proportions, it can watch these YouTube videos and map our movements onto its own body. But there was a catch. Internet videos are blurry and messy. The robot couldn't see the details, so they used upsampling. Think of this like your brain filling in the gaps of a fuzzy memory to make it vivid. They didn't just sharpen the pixels, they generated hyper-detailed descriptions of the physics in the video. This turned lifting the dumbbell into a rich data stream about grip angles and finger pressure. Suddenly, the entire internet became a training dojo. Part 1. The Imagination Engine. World Model. Now comes the Cortex part. They built a world model. This is the robot's imagination engine. You give it a text command, like pick up the red mug, and it doesn't move yet. First, it hallucinates a short video of what success looks like. Because it studied all those internet videos, it understands the physics of the world. It knows that if you push a mug, it slides. It knows gravity exists. This hallucinated video becomes the target. The robot literally sees the future it wants to create. Part 2. From dream to muscle memory. Inverse dynamics. But dreaming about a backflip is different than doing it. You need to translate the visual dream into muscle twitches. This is inverse dynamics. Forward dynamics is guessing what will happen if you move. Inverse dynamics is knowing what you want to see and figuring out which muscles to contract to make it happen. The robot analyzes its own dream frame by frame and calculates the exact joint angles and torques needed to match the video. They even used something called dynamic time warping. Since the robot's brain thinks faster than its body moves, this algorithm stretches time, keeping the robot's physical motions synced up with its mental simulation. The results? Zero-shot learning. By learning to dream, the robot got better at reality. On completely new tasks, things it had never practiced physically, success rates jumped from 54% to 73%. It nailed complex tasks like steaming a shirt or opening a sliding door. It still struggles with things like scrubbing dishes, tasks where you need to feel the force, not just see it. Vision isn't enough for everything, but the fact that it could attempt them at all is a massive leap in generalized intelligence. Conclusion: the self-teaching flywheel. Why does this change everything? Because we've moved from programming to parenting. We aren't writing code for every movement anymore. We are building a foundation model, a brain that learns from the collective experience of the internet. And, just like humans, once these robots can imagine success, they can practice on their own. They can try, fail, learn, and update the model for every other robot in the world. We are witnessing the birth of physical intuition in machines. If you want to keep exploring the line between Cortex and Code, make sure you subscribe. I'll see you in the next one.